Find the area enclosed by one of the petals of the curve r equals cos 3 theta. Okay, so this is one of these flower-looking curves. It looks a little something like this. Okay, obviously passing through the pole here, but you get sort of a propeller shape or flowers. We refer to these segments here as petals. Okay, so area enclosed by a single curve, this curve is going to have to intersect. And if you believe our picture, it intersects itself at the pole. Okay, but we should probably do a bit of work to justify that. And then we can work out the area using the integration formula. Alright, so, well, let's take a look at the Cartesian version of the curve. So, if I plot it Cartesian style, r cos 3 theta is going to run through cosine 3 times by the time we hit 2. Okay. And it actually traces over itself twice. Now you can see here that it's going to hit the pole. Okay. And, well, all we really need to do is get the area from one intersection of the pole to the next. Okay, and in particular, if we start drawing from one, come down around here, we hit the pole, then we enclose this loop. Then we go up and around, hit the pole again. And then here at pi -1, we're back to where we started, and then we go through the whole process again. Okay? So each one of these peaks and valleys, or hills and valleys we might say, represents drawing one petal. Okay? Going from pole to pole. So where does this happen? Well, where does r equal 0? Okay? So if cos 3 theta is equal to 0, when does that happen? Well, normally cosine is 0 at things like pi by 2 and 3 pi by 2. Okay. But we need to deal with cos 3 theta, so divide these by 3. So from pi by 6 to pi by 2, okay, that will be this loop down here, finally coming in to rest just as theta value comes up to pi by 2. Okay? So this is how we work out the bounds for our area. Okay? So the area enclosed by just one of the petals. Okay? And then if we wanted all of them, we could just multiply by 3 because there's only 3 petals. And then what do we need to do? 1/2 r squared d theta. So that's going to be 1/2 cos squared 3 theta d theta. Well, for a moment, let's just work out what the antiderivatives of cos 3 theta look like. Right? Because if we pull the 1/2 out of here, we'll have cos squared 3 theta. And then if we've got sort of a general antiderivative, we can plug in pi by 2 and pi by 3, take the difference. We know how to do this. Okay? Well, this is an even power of a sine or a cosine. Okay? So what we need to do is cleverly rewrite things. Remember, cosine 2x, or cosine squared x can be rewritten as 1 plus cosine 2x all over 2. Okay, just using trig identities. So we can replace this with 1 plus cosine, now it's going to have to be 2 times the 3 theta, so cosine 6 theta all over 2. Okay, integrate 1/2. We get theta over 2. And then integrating cosine 6 theta should give us sine 6 theta over 6, but also combine it with the 2, we get 12. Okay. So now our area is 1/2. Okay, evaluate this at pi by 2. Okay. And then subtract it evaluated at pi. Okay, so we work those out. 1/2, it'll be pi by 4. Now, 6 pi by 2 is 3 pi, and sine at 3 pi is 0, so we can just ignore that part. Okay. And then minus pi by 6 over 2, so that's going to be pi by 12, plus 6 pi by 6 is just pi. Sine at pi is again 0, so we can ignore that part. So I've got 1/2 pi by 4 minus pi by 12. I'm going to write it as 3 pi by 12 minus pi by 12. And so that'll be 1/2 2 pi by 12, or 2 pi by 24, or you just say pi by 12. And so that's the area of exactly one of those petals. Okay, this one down here, but they're all going to be the same because it's all the same sort of hill or valley, just shifted around a lot. And you can check the other ones can be done in the same manner. Okay, so our answer here is just pi by 12.